Hey everyone, this is Charlie, the co-founder and the principal of XCAM. Now we are happy to have Arvind to do the USACO Silver Live solution for this just finished December contest. Arvind, he's a ICPC, International College Programming Contest World Finalist. He has been teaching XCAM for several years. We are so happy to have him here to share the solution. Hey, Arvind, turning the stage to you.
Hey everyone. Um, yeah. Yeah. Yeah, I'll just first um give an overview, I guess. Okay. Yeah. Um, let me share my screen. Yeah, so this contest had three problems. I guess they were in roughly increasing order of difficulty. Um, and I'll go back to this later, but I think for many people, cake game was the easiest, and this was the hardest. Um, and yeah, these are like topics that ended up being the solutions, but I'll go over the problems. Yeah, so I'll change my screen share. Yeah, so the first problem, which I guess is the easiest for many of you, was the problem cake game. So basically there's there's a row of n cakes where n is even, and their sizes are A1 to AN. And Bessie and Elsie take turns, right? So either Bessie takes two adjacent cakes, um, and then kind of merges them so that it's the sum. So if like this is something Bessie might do. So if it's three here and it's five here, then Bessie might merge it and then it will become eight. And then Elsie, given all the cakes, will choose the leftmost or rightmost cake and then take it, right? We can go over some samples. So this is an example sample input. So for 40, 30, 20, 10. Um, I guess Bessie can merge these two first. So it becomes 40, 50, 10. Um, and then Elsie can take this 40, and then Bessie can merge these two. And then Bessie will get 60, and then Elsie will get 40. And then it's the similar thing for this, right? So I think, uh, yeah, so one thing that can be useful to look at is what are the subtasks? Yeah, I think this case is also kind of similar. Um, so the first subtask is where all the elements are equal, right? Um, so yeah, so let's consider the case where all the elements are equal, right? So the first one will be x. So you can assume they're x, 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 right? These are all the cakes. Um, and one thing you can assume is that they're just all one. Let's just assume they're ones because um, the solution will be the same. You'll just have to multiply by x, right? I guess there's an even number, so there'll be six. So let's look at some small cases for where there's ones, right? So if there's one cake that's one cake that's one, then in the case for n equals two, Bessie can merge these together, and then answer will be two. Um, and then in the case where n is equal to four, Bessie can merge these together, so it'll become 1, 2, 1. And then Elsie will take one of these, and then Bessie can merge these together. So the answer will be 3, right? And then we can look at 6 ones. So Bessie can merge these together. It will become 1, 1, 2, 1, 1. And then Elsie may take something in the edge. And then Bessie can merge two of them together. So it'll become 1, 3, 1. And then Elsie may take this, and Bessie will merge this. So this gives 4, right? So yeah. So notice that uh yeah, so here we have like n is like an even number, right? So we can kind of guess a pattern here, right? So like this is two, yeah, so we can guess in pattern just based on these cases. When n is 2, answer is 2, n is 4, answer is 3, n is 6, answer is 4. So the answer may be something like k plus 1, right? Good idea. Can you do that? Does that work? Um, I guess if you want, you can take a screenshot of this. I'll give like a few seconds. Okay, so I assume people have taken screenshots of this. And I'll also scroll down to the subtasks. Yeah, these are the subtasks. All the elements are equal. N is at most 10. N is up to 5,000. And the original constraints, I think it's like 10 to the 5 or um, 5 times 10 to the 5. Yeah, right. So yeah, so for the case where they're all equal, we see this kind of pattern. And then we can prove that the pattern actually works. Sorry, just give me one moment. Uh, yeah, so we can prove the pattern works. Sorry. Okay, I think it's fine. Yeah. So yeah, so there's a pattern that you can kind of like guess by looking at some samples, but you can prove it will work, right? Because LC will always take k minus 1 steps. So LC score is at least k minus 1, and then the sum of both of them will be 2k, right? So then that will mean that Bessie is at most k plus 1, right? So we know that when they're all equal, the answer is equal to k plus 1, right? Then we can kind of guess like how to do the original problem based on this, right? So we can look at, in this case, where this 2 came from. It came from the entire array. And then where did this 3 come from? It came from this array here. And then where did this 4 come from? You can keep tracing back. There's 3, 1, and then there's 2, 1, 1. And then there's 1, 1, 1, 1. So it came from here, right? Um, so in these cases, the answer came from some kind of subarray, right? Um, and then if you like look at these cases, uh, like Bessie scores like from this subarray of length 3. Bessie scores from this subarray of length 3. Yeah, and then here it's from this subarray of length 3. I guess these cases are the same. But one thing like you can kind of maybe try guessing is maybe the answer is some kind of subarray, right? So maybe Bessie like does all the operations here, and then LC does all the operations here, right? So maybe a reasonable guess, um, maybe a reasonable guess for this problem is that answer is the smallest subarray sum, right? And it turns out this is really short to implement, right? You can have prefix sums, and then each subarray is going to be of the form like pre I plus k minus pre I. Yeah, so this is maybe like 7 lines implementation. It doesn't hurt to like guess and just try it. And it turns out it works, right? Um, yeah, any questions? I can talk a little bit more about intuition about why it works. But yeah, okay. Yeah. So the idea is like, um, yeah, so consider you have like an array. Yeah, so this is how I did the problem. I didn't try proving it when I did it. I just guessed and it worked. But we can also, it's also good to be able to like understand why it works. So just consider a case. Um, yeah, So essentially, like during the process, like this will be merged into pieces. And Bessie doesn't want it's like Bessie doesn't want Elsie to be able to eat these pieces, right? So Bessie can start here. And then Elsie can pick one of these two ends, right? So if Elsie picks, I'll just change the color. So red is Elsie. So if Elsie picks this one, um, then it's a bad idea for Bessie to merge these two, right? Because if Bessie merges these two, then Elsie can take the entire thing, right? So if Elsie takes the leftmost, then it's better for Bessie to merge this with whatever's to the right, right? Um, and then Elsie will take one of these, um, and then Bessie will take the entire thing, right? Um, yeah, any questions? So essentially, Bessie picks the center in the beginning, and then whatever Elsie does in the beginning. So if Elsie picks the left, it forces Bessie to pick the right because Bessie doesn't want Elsie to have the big block. And then if Elsie picks the right, then Bessie will pick the left. Yeah. So basically, Elsie can force any subarray of length k plus 1 to be picked. Oh, how do you find k? So I just define n is equal to 2k. N is an even number. And then Bessie's thing is a k plus 1 length subarray. Yeah, that's how you define k. Any other questions? Right, great. I'll move to the next problem then. Uh, okay, yeah, yeah. Okay, yeah. This problem is called deforestation. I think my zoom is a bit off. Um, okay, yeah. So this is the deforestation problem. Um, yeah. Okay, so I guess the first sample input is covered. Yeah. So there's n trees, right? On a number line, and the ith tree is at some location on the number line. And then there's a bunch of constraints. So inside a range, there needs to be at least ti trees, right? And Farmer John wants to cut as many trees as possible, right? So I guess I'll just draw a very simple example. So if you have 3 trees and constraint ti um, equals 2, um, then this range has to have at least 3 trees inside, right? And then the goal is to find the maximum number of trees Farmer John can cut down. So in this case, Farmer John can just cut this one down. So then the answer is equal to 1, right? Yeah. Um, and there are some cases here. Yeah, yeah, wait, sorry. Yeah, I think this is the same case. Yeah, these are just some additional cases. Yeah, yeah, I guess I can draw like another case that's maybe more reasonable. So something like this and this. Uh, yeah, yeah. Um, so yeah, if ti is equal to 2 here, ti is equal to 2 here, then you can cut this tree, and then the answer will be 2, right? Yeah. Um, yeah, and just a reminder, we have kind of the usual constraint, n is up to 10 to the 5. So we might want something that's like O of n log n, right? Yeah, and the subtasks, one of them is nk up to 16. Other one is up to 1000, so maybe something n squared. And then the other one is kind of interesting. It's basically you need to have at least one tree inside each range. And then the last one is no additional constraints, right? So looking at the problem, we see like the coordinates are from -10 to the 9 up to 10 to the 9 like of everything, right? So maybe this will be something like, this might be -10 to the 8th, 10 to the 6th, and then maybe this is 1 and this is 2, right? But we only care about these values, right? So we can do index compression, right? So we can transform this input, for example, to like this range is from 1 to 4, and then this is 2, and then this is 3, right? So we can do index compression. So then after you do index compression, all the coordinates are up to 2n, right? Yeah. So there's this stuff with like -10 to the 9 up to 10 to the 9. So you don't have to actually worry about these. You can just index compress and assume all the coordinates are up to 2 times n, right? Yeah. Um, yeah. So I guess like this case is brute force, right? There's 2 to the 16 ways, um, 2 to the n or up to 2 to the 16 ways to cut trees. So this will be like k times 2 to the n. Um, yeah. So this is the brute force one. So let's look at so maybe this one is like n squared, but let's look at this case, this subtask, which is inputs 6 to 7, because that might give us useful intuition, right? So what subtask 6 to 7 is that uh, each range must have at least one tree, right? So each range must have at least one tree. So I'll move to OneNote. So this is problem 2. So one of the subtasks, sorry, one of the subtasks um, is ti is equal to 1 for all I, right? So remember a goal is to maximize number of cuts. Yeah, so you can view it this way. Equivalent way of viewing it is also equivalent to like minimize the number of trees that you keep. So that all these constraints are still satisfied. So you can look at an example. So I'm just going to talk about it from this perspective, where you minimize the number of trees. So if you have these two ranges, yeah, maybe you have something here, you have something here, and you have something here. You can decide to keep this one, right? Yeah. And I can do another case. Maybe you have like there's one case, there's another case. Of this one and this one. Um, so yeah, you want to keep this one because each range has to have at least one tree, right? Um, so we can do the following. So we can try processing things from left to right, and then try to see how we can minimize the number of trees, right? So goal, I guess if you think of these as points as segments, is to find min number of points. Sorry. Such that each segment contains a point. Right. So we can go from left to right. Yeah, and one interesting thing about this problem is that it's guaranteed that the forest initially satisfies these restrictions. So solution is guaranteed to exist, right? So let's look at this example again, this specific one, right? So I'll just draw it below. So there's a tree here, and there's a tree here, right? So it's always better to keep, like, between these two things, it's always better to keep this one because it's intersecting with this and it's intersecting with this. So one thing we can try is we can go from left to right. And then once we hit a right endpoint, we can check, yeah, we can check if it already contains a point. Yeah, we can check if it already contains a point. And if it does, then we're done. Otherwise, you include the rightmost point. Right? So the algorithm is go from left to right. And then when we reach a right endpoint of some interval, when we're at a right endpoint, it's always better to pick the rightmost one because that will intersect with more segments in the future, right? Pick latest tree, right? Yeah. So what we can do now is, yeah, we can do some kind of a sweep, right? So yeah, so our events will be like, yeah, yeah. So the events, yeah. So an event is when we go from left to right, we either add a point. So events, we either add a point or we reach the right endpoint. I guess I'll just reword this. So when we go from left to right, we either like see a point, or we reach a right endpoint. And then when we reach a right endpoint, we can see if there's already any points covering this. And if there's not, then we add the rightmost point. Right? Any questions how this algorithm works? So again, reminder this for ti equal to 1. Yeah, and then maybe you have like another line here, then a point here. And then when you're here, you already see that you have a point. So you don't need to do anything. And then when you're here, there's no point that's included. So then you can include this one. And when you see a point, basically when you're adding the rightmost point, you're looking at the maximum point that's still available. So when you see a point, you can add to a priority queue. And then when you add the rightmost point, you can just like keep track of the latest point that you have, and then remove it from the priority queue. So you use the priority queue to find the rightmost point. Yeah. So that's the idea for ti equal to 1. So that will give you the second to last subtask. And let's go over how to do it for general ti, right? Yeah, so the idea is go from left to right. And when you're at a right endpoint, you want to minimize the number of points you include, so just add the rightmost point that you see. So for general TI, we can do the following. Sorry. So let's say our points are like this. let's say a range is like this, another range is like this, points like this, and maybe this has like ti is equal to 3, and then this has ti equal to 3, and this has ti equal to 1, right? So we can still process from left to right, and it's always optimal to pick the points as right as possible, right? So from this endpoint, we pick these 3 points, and then for this endpoint, we see that already 2 points are there. So then we pick this point, right? So we shouldn't, this picking this point is better because there's this t equals 1 here, right? And then when we're at this t equals 1, our constraint's already satisfied, right? So the strategy here is to keep going from left to right. And then when you reach a right endpoint, keep adding the rightmost point until your constraint is satisfied. So I can write some pseudocode for this. So the idea is like, so basically your events, they're the same thing, see a point, and then reach right endpoint. And when you're seeing a point, when you're going from left to right, you can add to a priority queue. And then when you reach a right endpoint, basically it's like while total number of points less than ti, add biggest point. Right? So I'll write some pseudocode for this kind of. One sec. So it's going to look something like this. So you can iterate over the coordinates from 1 to 2n. And then if there are like any points in C, right? So if then you can add C to a priority queue. And then otherwise, like there might be pairs of the form LC that end at C. And then while num points in LC is less than T, like the TI for this thing, add largest point from the priority queue. Right? So the question is how can we check if the number of points in this range is less than or equal to T, right? So I guess the brute force way, you can check this in, you can find the number of points inside this range in O of n time, right? Just iterate over all the points. So then, and then you're going to add something to the priority queue at most n times. So then this will be roughly like O of n squared-ish, which is enough to pass this inputs 3 to 5 case, right? So to summarize this n squared algorithm, we're going to speed it up with a minor modification. You go from left to right, and then you process points, and then when you're at a right endpoint, you keep adding the rightmost tree that's available until the constraint is satisfied. I'll just summarize what we did up to here. So the goal was to maximize the number of cuts. So this is equivalent to minimizing the number of trees. And then our greedy algorithm is to go from left to right. And then when we're at a right endpoint, keep adding the rightmost point until the constraint is satisfied. So here we we add points for this first, then we add points for this, and then we check if we add points for this, right? And then basically we go from left to right, see what happened, what events happen at each coordinate. So if there's a tree at C, then you can add it to a priority queue where C is your coordinate. Otherwise, while the constraint is not satisfied, you keep adding the highest valued thing, right? Any questions? Yeah. So we'll talk about how to speed this up. So there's a data structure called a binary index tree. Um, yeah, so you can, yeah, it's a good thing to learn, but you can feel free to look it up after. But I'll just say what you can do is you can maintain an array, and then you can do operations of this form. So add AI plus equals X, and then query the sum of a range, right? And both of these operations can be done in log n time. Yeah, so I suggest looking this up. The implementation is actually very short. It's like 2 for loops. But essentially, instead of like iterating over all the points, all the trees to find the total number of points in the range, what you can do is you can, whenever you add a tree, you can add them to a binary index tree, right? So let's say these are your trees, basically adding +1 at a location. And then whenever you want to check if the number of points is less than ti, this is a range query, right? So this is L and C. You do a range sum query, right? Yeah. So this algorithm naively is O of n, but if you do the binary index tree, it'll be this part will be this querying will be log n. So the time complexity will be like linear in n and k times the log factor. Any questions about this problem? Yeah, I think there's also a way to do without a binary index tree. It's kind of complicated. I think this may be a simpler one that I'm aware of. But I think if you know policy-based data structures, like sorry, like ordered set, those kinds of things also work here. Okay, so I'll go over the third problem. Um, yeah, so this one's kind of hard. It's maybe the hardest one. Um, but yeah, I think it's harder to come up with, but algorithm is maybe a bit straightforward. I'll just go over it. So yeah, so there's a factory that can be described as an n by n grid of conveyor belts. So can either go left, right, up, down, or there's not a conveyor belt yet, right? So maybe the current state of it might look something like this. There's a conveyor belt here. And maybe there's something like this. So you can keep going in a cycle, right? Um, and they define a state to be unusable if when you're starting at the state, you can't leave, right? So for example, like, yeah, so they're just considering you have like these conveyor belts, consider like adding new conveyor belts to it, right? However you want. So a cell is usable if you can leave it, right? So this cell here is usable. If this was also a conveyor belt in the beginning, this cell is also usable. And these cells here are unusable, right? Yeah. Uh, so so this problem is related to given a conveyor belt. when you're adding new or given a grid of cells with conveyor belts, when you're adding new conveyor belts, trying to maximize the number of cells from which you can escape the grid, right? Yeah. So the exact problem is like initially the grid is empty, and then at each time step, a new conveyor belt is added, right? Then after each time step, you need to find what's uh, what's the maximum number of places from which I can exit if I add the conveyor belts in a certain way. I guess we can go over this example. Yeah. Oh, okay. Yeah. Um, Wait, I think I flipped something around. Just give me a sec. Uh, oh, okay, yeah, yeah, I was correct. Yeah. So minimum number of unusable, same thing as maximum number of usable, right? So minimum number of unusable in this case, let's say the conveyor belt is like this. Um, so yeah, um, yeah, so yeah, so these two are unusable. Oh yeah, and then this one is also unusable, right? This one is also unusable because you'll go here and then you'll keep cycling, right? And then for the rest of the cells, you can just do like left arrow here, down, left, right, right, right. So you can escape from all of these cells, right? So the answer is going to be 3 here, right? So let's look at the subtasks, right? Um, so the first subtask is n is up to 10. So maybe some kind of n to the sixth thing. Second one is n is up to 40. And then the last one is no additional constraints, um, right? So let's consider a set like a square with conveyor belts, right? Let's try to do a small case. Um, so let's say we have this thing and it already has its conveyor belts, right? Maybe this one is in a cycle, so you can't escape. Um, and then this one, you also can't escape from it, right? Um, yeah. Let's say this is the current state, um, right? And then basically how you can think of this is each thing that doesn't have a cell, you can add however you want these conveyor belts, right? So you can either add up, left, right, or down on any of these, right? Right? Um, so then the question is like, if you add all these up, down, left, rights, then from how many cells can you exit the grid, right? Um, and one way to think of this is like, uh, so you can exit the grid if from one of the boundaries you have something like this that points to the left, or points to the up on the top, right? So what you can do, you want to find the number of cells from which you can exit the grid, right? Goal to find number of cells from which you can exit the grid. And you can exit the grid if there's a path to the outside, right? So what you can do is you can do a DFS on the reverse graph. Right? So you can start from all the things in the boundary and then just run a DFS on the reverse graph. And this will give an O of n squared time. Um, it'll give you all the usable cells, uh, max number of usable cells. And then the number of queries is up to like n squared, right? Yeah, number of queries is up to n squared. So then this will be, yeah, this will be O of n to the fourth, right? Any questions about this? So what I'm basically saying is for all the cells that are empty, they have question marks, you can add a conveyor belt however you want. So you can think of these as their edges are pointing up, down, left, and right. And then you want to find the total number of cells from which you can escape the grid. And how you can do this is you can do a DFS on the reverse graph, starting from the boundaries. So then this will be n to the fourth. So that's enough to pass cases 6 and 7. Yeah. So let's talk about the full subtask. So this might yeah, so this is kind of maybe a bit tricky to observe the full subtask. So so let's just consider like what happens at the very end, right? Draw this a bit smaller. So at the very end, you have a bunch of things like this. Yeah. Yeah, so at the very end, the conveyor belt's already filled. And you can do a DFS on the reverse graph uh, to find which cells are usable, right? So maybe I'm just randomly picking. These are not necessarily right. But let's say like red is like usable cells, right? So at the end, what are all the usable cells, right? Right? And then you can consider like notice that like if a cell is usable at the end, it must have also been usable beforehand, right? This is just because as you're adding more and more edges, there's fewer and fewer options to exit the grid from each location, right? So because of this, as you reverse the process, there's only going to be more and more usable cells. So the idea is like process backwards. And then let's say, yeah, yeah. So if I change this one, it's not going to change anything if it's already unusable. But if I change something here, then I can start another DFS from here. And then maybe once this has been a reverse DFS, then I might visit more things, right? So the idea is process backwards, and then when removing conveyor belt, basically the things that I can reach the boundary from, they're kind of connected in some way. Maybe there's multiple connected pieces, but if something that we change is part of one of these connected pieces, then we can expand the usable cells. So removing conveyor belt, do another DFS if it can reach the boundary. Right? And yeah, so when you're doing another DFS on the graph, so I can just draw here. So maybe in the beginning, like the usable cells was like here. And then after you remove the first thing, maybe it's expanding here. And then after you remove the next thing, it's going to expand here. And then after you remove the next thing, it's going to expand here. So the sum of these sizes is O of n squared. Right? So the sum of the complexities of the DFSs is going to be O of n squared, right? Because yeah, each DFS is going to visit some amount of cells, and then the sum of the number of cells you visit is going to be O of n squared. Yeah, so the time complexity is O of n squared. Yeah, any questions? I guess I'll summarize this. Yeah, um, yeah, so this was the problem. The goal was to find the maximum number of cells from which you can exit the grid. And you can kind of view this as a graph problem. The things that we haven't put conveyor belts on, you can think of them as a graph with four edges in all directions. And then we want to see from how many of these can we exit the grid. This is the same as doing a DFS on the reverse graph. Yeah, yeah, yeah. So I can also explain some of the things I tried and failed on problem 3. Yeah, sure. Yeah. Um, so I think one trap, um, I don't know if this was the case for others. Yeah, I guess I'll just complete this. Yeah, so do DFS on reverse graph to see from which cells you can exit. Yeah, so I think one trap for me personally was, uh, so there's something called a functional graph. Um, so it's basically like each vertex has out degree 1. And I think this kind of graph may have showed up in some silver problems, also in some mock tests. So it has this kind of structure where each component is like a cycle, and then there's a bunch of trees that are in each cycle. So a functional graph might look something like this. Yeah. So yeah, I guess some things that I was trying to think was like if there's a cycle, uh, then like you're trapped inside here. So I think that didn't work. Or like this kind of intuition didn't really help too much. But it doesn't hurt to think about it. Um, yeah. Uh, but I guess for like the um yeah, so I guess like yeah, it's useful to try to do the small subtasks. Um, uh, yeah, so I guess for like n up to 10 or something, uh, yeah, so n up to 10, you can do something like you start from each cell and then you do DFS, and then see if you reach the outside. So this will be like O of n squared per cell. So then if you multiply this by n squared, this will be O of n to the fourth per query. Yeah, I did think of this when I was doing the contest too, in the beginning. Yeah, but then you can realize that, uh, like, yeah, I guess you can realize that you can see this as a graph. And then I think the key observation to, yeah, so you can see this as a graph. Um, I think one way I tried visualizing it is like the things on the boundary that you can reach the outside with, you can connect it to like a sink node. So it's basically you're trying to see if from each node it's possible to reach the sink node. Um, and it's kind of hard if you start a DFS from each vertex. But if you think of it this way, then if you reverse the edges from the sink node, it's just one DFS to see which vertices you can reach, right? I think the trickiest part was actually finding like actually doing the last subtask. So I guess one comment about this contest, I think, yeah, full solving the first and then full solving the second, and then getting the first two partials, I think that gives 800. So that's probably safe for passing. Um, yeah. But for the last one, I guess the way I guess I tried a bunch of different things, but one thing that worked is like the key idea is like if something is usable earlier, uh sorry, I guess like um yeah, so if something is unusable earlier, then even after you add edges, it's going to be unusable later. So if it's uh so if it's like usable later, then it'll be usable earlier. Yeah, so I think this is like the key observation that leads to the actual solution, um, where you have to like expand your usable things. Yeah, that's what we ended up doing here. Yeah, but I'd say this is kind of a hard one. Yeah. Um, yeah, and then once you come up with this observation that can lead you to think about which ones are usable, and then try to expand this as you go to earlier queries. Yeah, yeah, um, yeah, and I think it's also like somewhat tricky to uh, like convince yourself that this works, uh, but it does work because like you keep the visited like you like if something is visited, then it's always going to be visited. So the number of new things you visit is going to sum to n squared. Yeah. What do you think will be the cutoff for silver? Um, I can't say because it's not out, but I'll be surprised. I mean, I'll definitely be surprised if it's more than 750. I guess that's all I can say. Uh, oh no. Yeah, great. Thank you. I'll stop my share.